Welcome to Sleepy History and Mysteries, and another journey through the gentle landscapes of science and the human mind. Tonight, we're going to explore one of the most fascinating aspects of human experience: memory, and specifically, why our memories don't remain frozen in time like photographs in an album, but rather change and shift and reshape themselves throughout our lives. This is a story about the malleability of the past, about how what we remember today might not be quite the same as what actually happened years ago, and how the very act of remembering can transform a memory. It's a story that touches on neuroscience and psychology, on the architecture of the brain, and the nature of human consciousness itself. As you settle in for the evening, let's begin by considering what memory actually is at its most fundamental level. When we think about memory, we often imagine it working like a video camera, recording events as they happen and then playing them back when we want to remember. We might picture our memories stored away in the brain, like files in a cabinet, waiting unchanged until we need to access them again. But this intuitive understanding of memory turns out to be quite different from how memory actually works in the brain. Memory is not a passive recording device. It's not a static storage system. Instead, memory is an active, dynamic, reconstructive process that involves the brain assembling and reassembling information every single time we remember something. To understand why memories change over time, we need to understand how memories are formed in the first place. The process begins with encoding, the moment when an experience first makes its mark on your brain. When something happens to you, when you see something, hear something, feel something, your brain translates that sensory experience into neural activity. Neurons fire in particular patterns, forming connections with each other, creating what neuroscientists call a memory trace or an engram. But encoding isn't a simple one-step process. Your brain doesn't record everything that happens to you with equal fidelity. Instead, attention plays a crucial role in determining what gets encoded into memory. If you're paying close attention to something, if it's emotionally significant, if it connects to things you already know, it's much more likely to be strongly encoded. If you're distracted, if something is mundane and routine, it might barely register at all. Think about your commute to work or school. If you have a regular route you take every day, you've made that journey hundreds or thousands of times, yet you probably can't distinctly remember most individual trips. Why? Because your brain has learned that this is routine information, not worth the effort of detailed encoding. Your attention wanders to other things while you navigate on autopilot, and the specific details of any given commute simply don't get strongly encoded into memory. But if something unusual happened during that commute, if you saw an accident or encountered an old friend or witnessed something surprising, that would grab your attention. The emotional significance and novelty would ensure stronger encoding, and you'd be much more likely to remember that particular journey. After encoding comes consolidation, the process by which a newly formed memory becomes stable and more permanent. This is where things start to get really interesting, because consolidation isn't instant. It takes time, and during that time, memories remain vulnerable to disruption and change. The consolidation process happens at multiple levels in the brain. There's synaptic consolidation, which occurs relatively quickly, over hours to days, and involves the strengthening of connections between individual neurons. When you learn something new, the neurons involved in encoding that experience form new connections or strengthen existing ones. This happens through a process called long-term potentiation, where repeated activation of particular neural pathways makes those pathways more efficient and more likely to fire together in the future. The phrase that neuroscientists often use is neurons that fire together wire together. This captures the essence of how experiences create lasting changes in the brain's structure. The patterns of neural activity that represent a memory become physically instantiated in the architecture of neural connections. But there's also a larger scale process called systems consolidation, which unfolds over much longer timescales, from weeks to years. This involves the gradual reorganization of memories from one part of the brain to another, specifically from the hippocampus to the neocortex.
The hippocampus is a seahorse-shaped structure deep in the brain's temporal lobe, and it plays an absolutely critical role in forming new memories. We know this primarily because of a famous patient known as Henry Molaison, often referred to by his initials HM, whose case revolutionized our understanding of memory. Henry Molaison was born in 1926 and suffered from severe epilepsy. In 1953, when he was 27 years old, he underwent an experimental surgery to control his seizures. The surgeon removed portions of his medial temporal lobes on both sides of his brain, including most of his hippocampus. The surgery did help reduce his seizures, but it had a devastating and unexpected side effect. Henry lost the ability to form new long-term memories. After the surgery, Henry could remember events from his earlier life before the operation. He could hold a conversation and remember what was said for a few minutes. But he couldn't transfer new information from short-term memory into long-term storage. If you left the room and came back 10 minutes later, he wouldn't remember meeting you. Every day was new to him. disconnected from the previous day. He couldn't form new episodic memories, memories of personal experiences and events. Henry Molaison passed away in 2008, having lived for 55 years with this profound memory impairment. But his condition taught neuroscientists something invaluable about how memory works. The hippocampus, they learned, is essential for encoding new experiences and consolidating them into long-term memory. Without a functioning hippocampus, you cannot create new lasting memories of events and experiences, although other types of memory, like motor skills and habits, can still be learned. The hippocampus acts as a kind of memory organizer. When you experience something new, the hippocampus rapidly binds together all the different elements of that experience: the sights, sounds, smells, emotions, contexts into a coherent memory. It creates what we might think of as an index, pointing to all the different pieces of information stored in various parts of the cortex. But the hippocampus isn't meant to be the permanent storage site for your memories. Over time, through a process that happens largely during sleep, memories become gradually independent of the hippocampus. The connections between different cortical regions strengthen, and eventually, the memory can be retrieved without needing the hippocampus to coordinate the process. This systems consolidation process is crucial for understanding why memories change over time. Because as memories are transferred from the hippocampus to the cortex, they're not simply copied over like files being moved from one hard drive to another. Instead, they're actively reconstructed, and in that reconstruction, they can be altered. Recent research has revealed that the process is even more complex than originally thought. A study from MIT published in 2017 found that memories are actually formed simultaneously in both the hippocampus and the prefrontal cortex right from the beginning. However, the cortical memory remains silent for about 2 weeks, not contributing to recall during that time. The hippocampal memory is initially the one that gets used for retrieval, but gradually, over those 2 weeks, the cortical memory matures and becomes the primary trace used for remembering. This discovery challenged the traditional understanding that memories are first stored in the hippocampus and then slowly transferred to the cortex. Instead, it appears that both copies are created from the start, but they mature at different rates and serve different functions at different times. All of this consolidation happens most actively during sleep. When you sleep, your brain doesn't simply shut down. Instead, it enters into a remarkably active state of memory processing. During certain stages of sleep, particularly during slow-wave sleep, your hippocampus essentially replays the experiences of the day, reactivating the neural patterns that were formed during waking experience. This replay doesn't happen in real time. It's compressed, sped up, happening much faster than the original experience. As the hippocampus replays these patterns, it's coordinating with the cortex, helping to strengthen the connections that will eventually allow the memory to be stored more permanently in cortical networks. You can think of this as the brain practicing the memories, rehearsing them, integrating them with existing knowledge and experiences stored in the cortex. This is why sleep is so important for learning and memory. When you study for an exam or learn a new skill, Getting good sleep afterward helps consolidate those memories, making them more stable and easier to retrieve later. The architecture of sleep itself provides clues about its role in memory. Sleep is not a uniform state, but rather cycles through different stages, each with characteristic brain wave patterns and likely serving different functions. Non-REM sleep, particularly the deep slow-wave sleep stage, is especially important for consolidating declarative memories, facts, and events. During slow-wave sleep, your brain shows large, synchronized waves of electrical activity visible on an EEG. These slow oscillations reflect millions of neurons alternating between active and quiet states in a coordinated fashion. Nested within these slow oscillations are sleep spindles, bursts of rhythmic brain activity lasting a second or two. Sleep spindles appear to be particularly important for memory consolidation. The number and quality of sleep spindles correlate with how well people remember information they learned before sleep. When researchers have artificially boosted sleep spindles using targeted sounds or electrical stimulation, memory performance improved. The current model of how this works involves a careful choreography between the hippocampus and cortex. The slow oscillations that originate in the prefrontal cortex help coordinate the timing of hippocampal replay events and cortical sleep spindles. During the up phase of a slow oscillation, when cortical neurons are active, the hippocampus replays a memory. This replay is accompanied by high-frequency ripples, bursts of very fast brain activity in the hippocampus. These ripples, occurring during hippocampal replay, coincide with sleep spindles in the cortex. The spindles appear to create a window of increased plasticity in cortical circuits, allowing them to be modified by the information being transmitted from the hippocampus. Through this repeated coordination of slow oscillations, hippocampal ripples, and cortical spindles, information is gradually transferred from temporary hippocampal storage to longer-term cortical storage. REM sleep, the stage associated with vivid dreaming, also contributes to memory, though its role is somewhat different. REM sleep appears to be particularly important for integrating new information with existing knowledge, for extracting general principles from specific experiences, and for emotional processing. The brain is highly active during REM sleep, with activity levels similar to waking. The eyes move rapidly under closed lids, hence the name rapid eye movement sleep. Most muscles are paralyzed during REM, which prevents us from acting out our dreams. But the brain is busy, weaving together elements from recent experiences with older memories, often in bizarre and creative combinations that characterize dreams. Some researchers believe that dreaming itself, the conscious experience of dreams that sometimes occurs during REM sleep, may be related to this memory integration process. Dreams often incorporate elements from recent waking experiences, though usually in transformed and recombined ways. You might dream about people you saw during the day, but in completely different contexts, perhaps combined with places from your childhood or scenarios that never actually happened. This recombination and transformation might reflect the brain's work of integrating new memories with old ones, finding connections and patterns. The bizarre quality of dreams might be a side effect of this process, where the normal constraints and logic that govern waking thought are loosened, allowing freer association and combination of ideas. However, whether dreams themselves serve a function or are simply an epiphenomenon, a side effect of the brain's memory processing work, remains debated. What's clear is that the brain states associated with dreaming, particularly REM sleep, are important for certain types of memory consolidation and emotional processing. The emotional processing aspect of sleep is particularly interesting. REM sleep appears to help us process emotional experiences, potentially reducing their emotional intensity while preserving the memory of what happened. This might be why the phrase "sleep on it" has wisdom. Sleep can help you gain emotional distance from upsetting experiences. Studies have shown that people who get REM sleep after viewing disturbing images show reduced emotional reactivity when shown those images again compared to people who were kept awake or who only got non-REM sleep. The memories are retained, but they become less emotionally charged. This emotional decoupling might be crucial for mental health, preventing every upsetting experience from maintaining its full emotional impact indefinitely. Sleep deprivation, unsurprisingly, impairs memory. Missing a night of sleep after learning something new can significantly reduce how much you remember later. This is because the consolidation processes that should occur during sleep don't happen, leaving memories more fragile and prone to forgetting. Chronic sleep restriction, getting less sleep than you need night after night, also impairs memory function. Even if you don't feel particularly sleepy, cognitive functions including memory suffer. Students who pull all-nighters before exams typically perform worse than those who study less but sleep well. Athletes who get inadequate sleep show impaired motor learning. The modern epidemic of sleep deprivation, driven by work demands, technology use, and lifestyle factors, has profound implications for memory and learning. We are, as a society, not giving our brains adequate opportunity to consolidate what we learn during the day. Interestingly, naps can also support memory consolidation, particularly if they include slow-wave sleep. Even short naps can provide memory benefits, though longer naps that include complete sleep cycles are generally more beneficial. This is why some cultures that include afternoon siestas may be onto something from a cognitive perspective. The relationship between sleep and memory also works in the other direction. Memories can influence sleep. If you're trying to learn something difficult or are worried about an upcoming event, your sleep might be disrupted. The brain's attempts to process challenging or emotional information can interfere with normal sleep architecture. This bidirectional relationship highlights how interconnected sleep and memory are. They're not separate processes but deeply intertwined aspects of brain function. Understanding this connection helps explain why sleep problems are so often associated with memory difficulties and why addressing sleep issues can improve cognitive function. Beyond sleep's role in consolidation, let's explore how the passage of time more generally affects memory. There's a well-established curve of forgetting that describes how memory declines over time. This forgetting curve was first described by Hermann Ebbinghaus in the late 1800s in groundbreaking research where he served as his own experimental subject. Ebbinghaus memorized lists of nonsense syllables, combinations of letters that didn't form real words, to study pure memory without the influence of meaning or prior knowledge. He found that forgetting follows a predictable pattern. It's rapid at first, with much information lost within the first hour and day, then gradually slows, with information that survives the first few days likely to be retained much longer. This forgetting curve has been replicated countless times with various types of material. The general pattern holds. Rapid initial forgetting followed by a more gradual decline. However, the exact shape of the curve depends on many factors, including how well the information was learned initially, how meaningful it is, and whether it's rehearsed or reactivated. The mechanisms underlying forgetting are complex and not fully understood. Some forgetting likely represents actual loss of the memory trace through biological processes that weaken synaptic connections. But much forgetting appears to be retrieval failure rather than storage failure. The information is still there in some form, but you can't access it. This is demonstrated by the phenomenon of recognition being easier than recall. You might not be able to recall someone's name, but if you hear it, you recognize it immediately. The information was stored but couldn't be actively retrieved without a cue. Similarly, relearning information you've forgotten is typically faster than learning it initially, suggesting that traces of the earlier learning remain even if they're not consciously accessible. The tip of the tongue phenomenon is another example of retrieval difficulty. You know something, you can almost grasp it. Perhaps you know some features of it, like how many syllables it has or what letter it starts with, but you can't quite retrieve the complete information. This frustrating experience actually tells us something important, that accessing stored information requires successful navigation of retrieval pathways, and this process can fail even when the information is clearly stored. Context plays a crucial role in retrieval, as we discussed earlier. But it's worth elaborating on just how powerful context can be. The famous encoding specificity principle, proposed by Endel Tulving, states that memory is improved when the context at retrieval matches the context at encoding. This applies to both external environmental context and internal state context. The scuba diving study mentioned earlier is a dramatic demonstration, but the effect occurs in more subtle ways all the time. If you learn information in a particular room, you might find it easier to remember that information when you're back in that room. This has practical implications for students. If you're going to take an exam in a particular room, studying in that room or in a similar environment might give you a slight advantage by making the retrieval context match the encoding context more closely. However, the effect is usually modest, and there are advantages to studying in varied contexts, which makes memories less dependent on any particular context. The state-dependent learning effect can be quite strong for some states. Information learned while under the influence of alcohol is remembered better when under the influence of alcohol again, though of course this doesn't mean studying drunk is a good idea, since alcohol impairs encoding and cognition in many other ways. Similar effects have been shown for caffeine, mood states, and even body position. Music can serve as a powerful context cue. People often report that hearing a song they haven't heard in years brings back vivid memories of when they used to listen to that song. The music recreates part of the context in which memories were formed, facilitating their retrieval. Smells are particularly potent memory cues, perhaps because olfactory information is processed in brain regions close to the hippocampus and amygdala. A particular scent can trigger unexpectedly vivid memories from long ago. These context effects reveal something fundamental about how memory works. Memories are not stored as isolated items, but as parts of networks of associated information. Retrieving a memory involves activating this network, and anything that activates part of the network makes it easier to activate the rest. This associative nature of memory is why mnemonic techniques work. Memory champions who can memorize decks of cards or long lists of numbers aren't using fundamentally different memory systems than the rest of us. Instead, they use strategies that leverage the associative structure of memory, creating elaborate connections between what they're trying to remember and information they already know well. The method of loci, one of the oldest mnemonic techniques, involves imagining placing items to be remembered at locations along a familiar route. When you later mentally walk that route, each location serves as a retrieval cue for the associated item. This works because it creates rich, organized associations, and it leverages spatial memory, which humans are generally quite good at. Chunking, mentioned earlier in the context of working memory, also works by creating meaningful associations. Random digits are hard to remember, but if you can group them into dates or meaningful numbers, they become much easier to retain. The information hasn't changed, but the organization and associations have. Understanding these principles of memory organization helps explain both why we forget and how we can improve our memory. Isolated, meaningless information with no connections to existing knowledge is hard to encode and easy to forget. Rich, meaningful information connected to many other things we know is easier to learn and more resistant to forgetting. But here's where things get particularly interesting for our exploration of why memories change. Each time a memory is reactivated, whether during sleep or during waking recall, it doesn't just get replayed unchanged. Instead, it enters what neuroscientists call a labile state, a temporarily unstable state where the memory becomes vulnerable to modification. This process is called reconsolidation, and its discovery has fundamentally changed how we think about memory. For many decades, neuroscientists believed that once a memory was consolidated, once it had been transferred into long-term storage, it became permanent and unchangeable. Memories might fade over time, might become harder to access, but the memory trace itself was thought to be stable. The reconsolidation finding overturned this view. It showed that retrieving a memory, bringing it back into conscious awareness, actually destabilizes the memory. It's as if opening the file causes it to become editable again. And during this window of lability, which lasts for several hours after recall, the memory can be updated, modified, or even disrupted. The first modern demonstration of reconsolidation came from a study published in the year 2000 by Karim Nader and colleagues. They worked with rats that had been trained to associate a particular sound with a mild electric shock, a standard fear conditioning procedure. The rats learned to freeze in fear whenever they heard the sound, because they had formed a memory linking that sound with the unpleasant shock. Nader and his team did something clever. They let the memory consolidate fully, waiting until the fear memory was stable and long-term. Then they played the sound to reactivate the memory, and immediately afterward, they injected a drug into the rat's amygdalas, a brain region crucial for emotional memories. The drug they used was anisomycin, which blocks protein synthesis, the creation of new proteins in cells. What they found was striking. The rats that received anisomycin after their memory was reactivated later showed much less fear when they heard the sound again. It was as if the memory had been weakened or partially erased. Critically, rats that received the drug without first reactivating the memory showed normal fear responses. And rats that received the drug many hours after reactivation also showed normal fear. The drug only disrupted the memory if it was given during a specific time window after the memory was recalled. This demonstrated that recalling a memory makes it vulnerable again, putting it back into a state where protein synthesis is required to reconsolidate it, to restabilize it for long-term storage. If protein synthesis is blocked during this reconsolidation window, the memory is weakened. Since that landmark study, reconsolidation has been demonstrated in many different species, from sea slugs to humans, and across many different types of memories. The basic principle seems to be a fundamental feature of how memory works. Memories are not permanent recordings, but rather dynamic constructions that are rebuilt each time they are recalled. But why would the brain work this way? Why would evolution produce a memory system where remembering something makes it vulnerable to change? Wouldn't it be better to have perfectly stable, unchanging memories? The answer appears to be that the flexibility of memory is actually a feature, not a bug. Memories need to be updated to remain useful. The world changes, and your knowledge needs to keep pace with those changes. If you learn that a certain restaurant serves excellent food, that memory guides your behavior. But if the restaurant changes ownership and the food quality declines, you need to be able to update your memory to reflect this new reality. Reconsolidation provides a mechanism for incorporating new information into existing memories, keeping them current and relevant. Think about your memory of your childhood home. If you moved away from it at some point, that memory has probably been updated many times. Maybe you've seen photos from that time, and elements from those photos have been incorporated into your mental image of the house. Maybe you've talked with family members about events that happened there, and their recollections have influenced yours. Maybe you've even visited the house years later and been surprised by details you'd forgotten or remembered differently. Each time you've recalled that memory of your childhood home, you've had an opportunity to update it, to incorporate new information, to see it from a more mature perspective, to integrate it with your broader life narrative. This updating process means your current memory of that house is probably different in many ways from your memory of it when you first moved away. Research has shown that reconsolidation is particularly robust when there's something new to learn, some mismatch between what you expected and what you're currently experiencing. This makes sense from a functional perspective. If nothing has changed, if everything is exactly as you remember it, there's no need to update the memory. But if there's new information, if your prediction based on memory doesn't match reality, that's when the memory becomes labeled and can be modified to incorporate the new information. This brings us to one of the most fascinating and slightly unsettling aspects of memory. False memories, memories of things that never actually happened, or memories that differ significantly from the actual events. The pioneering researcher in this field is Elizabeth Loftus, a psychologist whose work over the past several decades has demonstrated just how malleable and unreliable memory can be. Born in 1944, Elizabeth Loftus received her PhD in cognitive psychology from Stanford University in 1970 and has since become one of the most influential researchers in understanding memory malleability and the creation of false memories. One of Loftus's most famous experiments was conducted with John Palmer in 1974. They showed participants videos of car accidents and then asked them questions about what they had seen. But they varied the wording of the questions in subtle but important ways. Some participants were asked, "How fast were the cars going when they hit each other?" Others were asked, "How fast were the cars going when they smashed into each other?" The only difference was one word, hit versus smashed. That single word made a significant difference. Participants who heard smashed estimated much higher speeds than those who heard hit. Even more remarkably, when participants were brought back a week later and asked whether they had seen broken glass in the video, those who had been asked about the cars smashing were more likely to say yes, even though there was no broken glass in the video at all. This demonstrates what Loftus called the misinformation effect, the tendency for post-event information to alter memory for the original event. The word smashed suggested a more violent collision, and this suggestion apparently became incorporated into participants' memories of what they had seen, even creating false memories of broken glass that wasn't there. The misinformation effect has been demonstrated in countless studies since then. If you experience an event and then later receive misleading information about that event, your memory for the original event can be changed. The misleading information can come from many sources: suggestive questions, conversations with other witnesses, media reports, or even your own inferences and assumptions. The mechanism appears to involve the reconsolidation process we discussed earlier. When you recall a memory and are simultaneously exposed to new information, that new information can be incorporated into the memory as it reconsolidates. The original memory and the new information become blended together, and you may no longer be able to distinguish what you actually experienced from what you learned later. This has profound implications for situations where accurate memory is crucial, particularly in the legal system. Eyewitness testimony, which juries often find very compelling, can be surprisingly unreliable. Witnesses can be entirely sincere, completely confident that they remember events accurately, and still be wrong. Elizabeth Loftus has testified as an expert witness in hundreds of court cases, often explaining to juries how memory works and why eyewitness confidence doesn't necessarily indicate eyewitness accuracy. Her work has been controversial at times, particularly when she has testified in defense of people accused of serious crimes, but it has been influential in bringing scientific understanding of memory into the legal system. Loftus didn't stop at demonstrating that details of memories could be changed. She went further, investigating whether entirely false memories for complete events could be implanted in people's minds. This research required careful ethical consideration, as you can't ethically traumatize people with false memories of terrible events for the sake of an experiment. So Loftus and her colleagues developed what became known as the lost in the mall technique. They worked with families and asked older family members to describe actual events from a younger family member's childhood. But they also created one false event, a story about the person getting lost in a shopping mall as a child, being frightened and upset, and eventually being found by an elderly person and reunited with the family. This false event was presented to participants mixed in with the true events, and participants were asked to recall what they could about all of these supposed childhood experiences. Remarkably, about a quarter of participants came to remember the false event. They didn't just say they thought it might have happened. They provided detailed descriptions, adding elements that hadn't been suggested to them, elaborating on the false memory with sensory details and emotional reactions. When these participants were later told that one of the events was false and asked to identify which one, many of them couldn't tell which memory was real and which was implanted. The false memory felt just as real, just as vivid, as their genuine memories. This finding has been replicated many times with various types of false events. Researchers have successfully implanted false memories of elaborate childhood experiences, of meeting Bugs Bunny at Disneyland, which would be impossible since Bugs Bunny is a Warner Brothers character, not a Disney character, of being attacked by an animal as a child, of committing crimes they never committed. The technique generally involves some combination of suggestion from an authority figure or trusted person, encouragement to imagine the event in detail, and repeated attempts to recall the event. The process of imagination appears to be particularly powerful in creating false memories. When you imagine an event vividly, picturing the details, thinking about how you would have felt, the act of imagination creates neural activity similar to actually experiencing the event. If this imagined event is recalled multiple times, it can be consolidated into memory just like a real experience, and you may lose track of the fact that it was imagined rather than experienced. Loftus's work has been especially important and controversial in the context of recovered memories of childhood abuse. In the 1980s and early 90s, there was significant attention to cases where adults in therapy appeared to recover previously forgotten memories of childhood sexual abuse. Some therapists used techniques like hypnosis, guided imagery, and repeated encouragement to remember, believing that traumatic memories might be repressed and needed to be brought to light for healing to occur. Loftus and other memory researchers raised concerns that some of these techniques might actually be creating false memories rather than recovering genuine ones. They pointed out that the same processes that created false memories in laboratory studies, imagination, suggestion, repeated recall attempts, were present in some therapeutic approaches. They noted that memory doesn't work like a video recorder that might have some tapes hidden away. Instead, memory is reconstructive and malleable. This led to what became known as the memory wars, a heated debate between those who believed that traumatic memories are often repressed and can be accurately recovered, and those who emphasize the malleability of memory and the ease with which false memories can be created. It's important to note that this debate isn't about whether childhood abuse happens, which tragically it does, or whether it can have lasting psychological effects, which it certainly can. Rather, the debate centers on the reliability of memories, particularly memories that are recovered after long periods of not remembering them, especially when those memories are recovered using suggestive therapeutic techniques. The scientific consensus that has emerged from decades of research is nuanced. Yes, memory is fallible and can be influenced by suggestion. False memories can be created, and they can feel completely real to the person experiencing them. However, it's also true that people can fail to think about or discuss traumatic experiences for long periods and then later remember them, and that these memories can be accurate. The challenge is that there's no reliable way to distinguish a genuine recovered memory from a false one based solely on how the memory feels to the person experiencing it. The practical implication is that we should be cautious about techniques that might create false memories, while also taking seriously reports of abuse and not dismissing them simply because they involve recovered memories. It's a difficult balance, and one that highlights the real-world importance of understanding how memory works. Now, let's consider another fascinating phenomenon that demonstrates memory's reconstructive nature: childhood amnesia, also called infantile amnesia. This is the inability of adults to remember events from the first few years of life, typically before the age of 3 or 4. Think about your own earliest memory. For most people, memories before age 3 are completely absent, and memories from ages 3 to 7 tend to be sparse and fragmentary. You don't remember learning to walk or learning to talk, despite these being major developmental milestones. You probably don't remember your first or second birthday. Even significant events from early childhood may be forgotten. This is puzzling in some ways. Young children clearly can form memories. A 3-year-old can remember what they did yesterday, can recognize familiar people and places, can learn new skills. So why can't adults remember being 3 years old? Sigmund Freud, who coined the term infantile amnesia in the early 20th century, believed it was due to repression of psychosexual content from early childhood. Modern neuroscience has better explanations that don't invoke Freud's psychoanalytic theories. One factor is the development of the brain regions involved in memory formation. The hippocampus and prefrontal cortex, which are crucial for forming and retrieving autobiographical memories, continue to develop throughout childhood. In very young children, these structures are not yet mature, which may limit the encoding and consolidation of lasting episodic memories. However, this doesn't fully explain childhood amnesia, because children themselves can remember events from earlier in their lives. If you ask a 5-year-old about something that happened when they were 3, they may well remember it. But if you ask that same person about the same event when they're 15, they'll likely have forgotten it. So it's not simply that the memories were never formed. They were formed but then lost. Recent research has identified neurogenesis, the creation of new neurons, as a possible contributor to childhood amnesia. The hippocampus is one of the few brain regions where new neurons continue to be generated throughout life, but the rate of neurogenesis is much higher in infancy and early childhood. Studies in mice have shown that increasing neurogenesis leads to increased forgetting of previously formed memories. The new neurons integrate into existing neural circuits, and in doing so, they appear to disrupt the connections that represent old memories. This makes sense during development when the brain needs to be flexible and plastic, able to adapt rapidly to new information. But it comes at the cost of forgetting earlier experiences. As neurogenesis slows down with age, memories become more stable. This may be why adults retain memories formed after early childhood more successfully than memories formed during it. Another factor in childhood amnesia is the development of language and a sense of self. Autobiographical memory isn't just about recording events. It's about creating a narrative of your life, a story of who you are and what you've experienced. This requires a concept of self as a continuous entity that persists through time. It requires language to encode experiences in a form that can be verbally recalled and described. Young children, particularly those under 3, don't yet have a fully developed sense of self as a continuous being with a past, present, and future. They live very much in the present moment. As Childertechniquisen develop language and self-awareness, usually around ages 3 to 5, they become better able to encode experiences in a form that can be retained and retrieved over long periods. Cultural factors also play a role. Research has shown that children from cultures with more elaborative storytelling traditions, where parents frequently talk with children about past events and encourage detailed recollection, tend to have earlier first memories and more extensive childhood memories than children from cultures with less emphasis on personal narrative. There's something bittersweet about childhood amnesia. Those early years are formative. They shape who we become in fundamental ways. The attachment relationships we form, the early experiences we have, all of this influences our development. Yet we cannot consciously access most of this foundational period of our lives. The person we were as a toddler is lost to us, knowable only through photographs, through stories others tell us, through perhaps some vague impressions and feelings we can't quite place. This highlights another important aspect of how our memories work and change: the role of external memory aids and social memory. Your memories don't exist solely in your own brain. They're also distributed across photographs, journals, souvenirs, and the memories of other people who shared experiences with you. When you look at a photograph from an event in your past, you might think you're accessing your memory of that event. but often your memory has been shaped by the photograph itself. You may be remembering the photograph as much as or more than the actual event. The photograph provides a stable external representation that influences and stabilizes your internal representation. This is particularly true for childhood events. You may have what you think is a memory of your third birthday party, but actually, what you're remembering is stories you've been told about it and photographs you've seen, all woven together into something that feels like a personal memory but is actually a reconstruction based on external sources. This phenomenon extends to shared memories between people. When you've experienced something with another person and you talk about it later, your memories influence each other. You might remember different details, and in discussing the event, those details get merged. Perhaps you remember what happened, but your friend remembers when it happened, and together you construct a more complete account than either of you had individually. But this social aspect of memory also means that memories can be shaped by group dynamics. If several people are all talking about a shared experience, the most confident or dominant person in the group may end up influencing everyone else's recollections. If someone confidently asserts that a particular detail was present when it actually wasn't, others may come to incorporate that false detail into their own memories. This brings us to an important question. If memories are so malleable, so subject to distortion and change, can we trust them at all? Are memories essentially fictional stories we tell ourselves about the past? The answer is subtle. Yes, memories are reconstructive and can be inaccurate. Yes, false memories can be created, and our memories can change over time. But this doesn't mean that all memories are equally unreliable or that memory is useless. Generally speaking, the gist of our memories tends to be more accurate than specific details. You might not remember exactly what you had for dinner last Tuesday, but if you remember having dinner with a particular friend, that broad fact is probably accurate even if the specific details of what you ate or what you talked about have faded or been distorted. Emotionally significant events tend to be remembered better than mundane ones, though even emotional memories are subject to distortion. The feeling of vividness and certainty that often accompanies emotional memories doesn't necessarily guarantee their accuracy, but emotional significance does promote stronger encoding and often more robust memory. There's also the concept of flashbulb memories, vivid and detailed memories of learning about significant public events, like where you were and what you were doing when you heard about a major news event. People often report that these memories feel crystal clear and unchanging, as if the significance of the event somehow caused perfect recording. However, research on flashbulb memories has shown that they're subject to the same distortions as other memories, despite the confidence people feel in them. Studies that have tracked people's memories of events like the September 11, 2001 attacks have found that people's recollections change over time, even though they feel certain that they're remembering accurately. One of the most famous studies of flashbulb memories was conducted by Ulrich Neisser and colleagues, examining memories of the Challenger space shuttle explosion in 1986. They asked college students to write down, the day after the disaster, exactly how they had heard the news and what they had been doing. Then, 3 years later, they asked the same students to recall the event again. Many of the students' 3 year later recollections were quite different from what they had written the day after the event. Yet when shown their original accounts, students were often shocked and insisted that their current memory must be correct and their written account must have been wrong. The vividness and confidence of their current memory overrode the actual documented evidence of what they had originally recalled. This overconfidence in memory is a consistent finding in memory research. People tend to be more confident in their memories than the accuracy of those memories warrants. We feel like we're remembering accurately, and this subjective feeling of certainty doesn't necessarily correlate well with objective accuracy. This is particularly problematic in legal contexts, but it affects everyday life as well. Arguments between friends or family members about what happened in the past often hinge on different recollections, with each person absolutely certain that their memory is correct. Understanding that memory is reconstructive and fallible might help such arguments be less acrimonious, though it doesn't necessarily resolve them. Despite all these limitations and vulnerabilities, memory serves us remarkably well most of the time. We navigate our world using knowledge and experiences from the past. We recognize people and places. We learn from experience and adjust our behavior based on what we remember about the consequences of past actions. The flexibility of memory, its reconstructive nature, while it opens us up to errors and false memories, also provides important adaptive advantages. Memory that can be updated allows us to learn continuously from experience. Memory that integrates new information with old allows us to extract patterns and regularities from our experiences, to develop general knowledge from specific instances. Consider how you learn a new route through a city. The first time you take that route, you pay close attention to landmarks and turns. You might even get lost or make wrong turns. Each time you take the route again, your memory of it becomes more refined. You notice which landmarks are actually useful and which aren't. You figure out which turns are crucial and which are obvious. Eventually, you don't remember a sequence of specific trips. Instead, you have a general schema of the route, an abstracted representation that guides your behavior without requiring you to consciously recall specific past journeys. This abstraction process, where specific episodic memories become generalized knowledge, is one of the important functions of systems consolidation and memory transformation over time. Your memory system doesn't just store individual experiences. It extracts meaning and patterns from those experiences to build up your general knowledge of the world. This is why students are often told to study material over multiple sessions rather than cramming everything into one session. Distributed practice, spacing out your study sessions with sleep in between, allows each study session to serve as a form of memory retrieval and reconsolidation. Each time you retrieve information, you're strengthening it, and you're also having an opportunity to integrate it with other knowledge, to see it from slightly different perspectives, to encode it more richly and durably. The process of retrieval itself strengthens memory, a phenomenon called the testing effect or retrieval practice. When you actively try to recall information, rather than simply rereading it, you're engaging in a deeper form of processing that leads to better long-term retention. This is one of the most robust findings in educational psychology, yet it's often underutilized in actual learning contexts. The testing effect works partly because retrieval is itself a learning event. Each time you successfully retrieve information, you're reinforcing the pathways that allow you to access that information. You're also updating the memory in light of your current context and understanding, which helps you integrate it with other knowledge. But retrieval can also introduce errors. If you retrieve information incorrectly and don't realize your mistake, you can end up strengthening an incorrect memory. This is why feedback is important in learning. You need to know when your retrieval is accurate and when it's not, so you can correct errors rather than reinforcing them. The relationship between memory and emotion deserves more detailed exploration. Emotional experiences are generally remembered better than neutral ones. This makes sense from an evolutionary perspective. If something made you feel strong emotion, whether fear, joy, anger, or sadness, it's probably something important that you should remember. Emotions serve as a signal of significance. The amygdala, an almond-shaped structure in the temporal lobe, plays a crucial role in emotional memory. When you experience something emotional, the amygdala becomes active and influences the hippocampus and other memory systems, enhancing the encoding and consolidation of that experience. Stress hormones like cortisol and adrenaline, which are released during emotional events, also affect memory. In moderate amounts, these hormones enhance memory consolidation. This is why many people have vivid memories of stressful or emotionally intense events. The emotional arousal essentially tells the brain, "This is important. Remember it." However, extreme stress can have the opposite effect, potentially impairing memory formation. This is one reason why memories from highly traumatic events can sometimes be fragmented or incomplete. The stress system can become so activated that it disrupts the normal processes of memory encoding. There's also a phenomenon called mood-congruent memory, where your current emotional state influences what you remember. If you're in a happy mood, you're more likely to recall happy memories. If you're feeling sad, sad memories become more accessible. This happens partly because emotions serve as retrieval cues. The neural and physiological states associated with an emotion can help reactivate memories that were encoded in similar states. This creates a potential feedback loop. If you're depressed, you're more likely to recall negative experiences and interpret neutral experiences negatively, which reinforces the depression. Cognitive behavioral therapy for depression often involves breaking this cycle by helping people notice and challenge biased recall and interpretation patterns. Another fascinating aspect of memory change over time relates to the concept of schema. A schema is a mental framework or template that represents our knowledge about a particular domain. We have schemas for common situations like going to a restaurant or attending a lecture. These schemas are built up from many individual experiences and represent the typical or expected pattern of events. Schemas are useful because they allow us to navigate familiar situations efficiently. You don't have to figure out from scratch what to do in a restaurant. Your restaurant schema tells you that you'll be seated, given a menu, order food, eat, pay, and leave. This knowledge guides your behavior without requiring conscious thought. But schemas also influence memory in important ways. When you experience an event that fits a schema, you tend to remember the event as being more schema consistent than it actually was. If something unusual happened that didn't fit the schema, you might not encode it well, or you might later remember the event as more typical than it was. For example, if you go to a restaurant and have an unusual interaction with your server, you might remember it for a while. But over time, your memory of that dining experience might become more schematic, more like a typical restaurant visit, as the unusual details fade and are replaced by schema-consistent expectations. This has been demonstrated in many experiments. If people read a story that contains some details that are inconsistent with relevant schemas, they're likely to later remember schema-consistent details that weren't actually in the story and forget or normalize the schema-inconsistent details that were there. This schema-based reconstruction is particularly evident when it comes to memories from long ago. The more time passes, the more your memories tend to drift toward being schema-consistent. The specific, distinctive details that made an event unique fade, and what remains is a more generic, typical version of that kind of event. However, very distinctive or surprising events, especially if they're emotionally significant, are more resistant to this schema-based normalization. If something really unusual and important happened, it's more likely to be retained in memory with its distinctive features relatively intact. The selectivity of memory, what we remember and what we forget, is itself revealing. We don't remember everything equally. Memory has biases and tendencies that shape what from our past remains accessible to us. One well-documented bias is the positivity bias in autobiographical memory, especially pronounced in older adults. When people recall their past, they tend to remember more positive events than negative ones, and their memories of past events tend to be more positive than their actual experiences were at the time. This isn't just wishful thinking or deliberate distortion. It appears to reflect genuine differences in how positive and negative information is processed and retained over time. The mechanisms aren't entirely clear, but it may relate to the functions of autobiographical memory. Memory isn't just about accurate record keeping. It's about maintaining a coherent sense of self, regulating emotions, and using the past to guide the future. A life story that's overwhelmingly negative would be demoralizing and might make it harder to maintain motivation and well-being. Some degree of positive bias in memory may serve important psychological functions, helping us maintain resilience and a reasonably positive self-concept, even in the face of life's inevitable difficulties and disappointments. However, this positivity bias isn't universal. People with depression often show the opposite pattern, remembering more negative events and interpreting ambiguous past events more negatively. This illustrates how memory is intertwined with current psychological state and how it can both reflect and reinforce patterns of thinking and feeling. The reminiscence bump is another interesting pattern in autobiographical memory. When older adults are asked to recall events from their lives, They show a disproportionate number of memories from adolescence and early adulthood, roughly ages 10 to 30. Events from this period are remembered more than would be expected based on how long ago they occurred. There are several explanations for this reminiscence bump. One is that this is a period of many firsts and many formative experiences. You have your first romantic relationship, perhaps go to college, start a career, maybe get married or start a family. These novel and significant events are encoded strongly and remain accessible. Another explanation is that this is a critical period for identity formation. The experiences you have during adolescence and early adulthood play a crucial role in shaping your sense of who you are. Memories from this period may be retained better because they're central to your life narrative, to your understanding of yourself. Yet another factor is that people tend to think about and talk about this period of their lives more than other periods. These memories get rehearsed more often, which helps maintain them. When you tell stories about your past, you're more likely to tell stories from this formative period, and each retelling reinforces the memory. The rehearsal and retelling of memories raises important questions about how narratives shape memory. When you tell a story about your past, you necessarily select certain details to include and omit others. You structure the events into a coherent narrative with a beginning, middle, and end. You might emphasize certain aspects and downplay others to make the story more interesting or to convey a particular message or theme. Each time you tell the story, you're likely to tell it in a similar way, perhaps even using some of the same phrases. And each retelling reinforces this particular version of events. Over time, the story you tell may become the memory you have, even if the story has drifted away from the original experience. This is especially true for important life events that you've recounted many times. Your memory of your wedding day, for example, or the birth of a child or a significant trip, these memories have probably been shaped by all the times you've talked about these events, looked at photos, thought about them, integrated them into your life story. In some cases, you might not really remember the original experience anymore. Instead, you remember the story you've constructed about the experience, a story that's been refined and polished through multiple retellings. The memory has become narrativized, transformed from a direct experiential record into a story about an experience. This process is neither good nor bad. It's simply how memory works. The narrativization of memory serves important functions. It helps us make sense of our experiences, extract meaning from them, and integrate them into a coherent life story. But it also means that our memories of significant events may be quite different from the original experiences in ways we're not aware of. Collective memories, memories shared by groups or even entire societies, show similar patterns. Historical events become narrativized and mythologized over time. Details are selected, emphasized, or omitted to create a story that serves particular functions for the group. Different groups may remember the same events quite differently because the narratives they've constructed around those events serve different purposes and emphasize different aspects. This is evident in how nations remember their histories. Founding myths, important wars, periods of struggle or triumph These are remembered not necessarily with perfect historical accuracy, but in ways that help define national identity and values. The collective memory is shaped by textbooks, monuments, commemorations, films, and countless other cultural practices that reinforce particular versions of the past. Understanding that both individual and collective memories are reconstructive and subject to change doesn't mean that truth doesn't matter or that all versions of the past are equally valid. Historical evidence, documents, physical artifacts, these provide external checks on memory that can help us evaluate the accuracy of our recollections. But it does mean we should approach memory with appropriate humility. We should be aware that what feels like a clear, certain memory might not be entirely accurate. We should be open to evidence that might contradict our recollections. We should be careful about making important decisions based solely on memory, especially for details rather than the overall gist of events. In practical terms, if something important depends on accurate memory, it's wise to create external records. Write things down, take photos, keep documents. These external memory aids can help counteract the natural malleability of human memory. At the same time, we shouldn't become paralyzed by skepticism about memory. Yes, memory is imperfect, but it's also remarkably functional. We successfully use our memories to navigate complex social and physical environments every day. We maintain relationships based on memories of shared experiences. We build careers based on knowledge and skills accumulated through remembered learning experiences. The goal isn't to achieve perfect memory, which may not even be possible or desirable. The goal is to understand how memory works, to be aware of its strengths and limitations, and to use this understanding to think more clearly about the past and how it relates to the present and future. One final aspect of memory change that's worth considering is how memory relates to personal identity. We often think of memory as essential to who we are. Your memories make you uniquely yourself. They're the record of your life and experiences that no one else has. This intuition is supported by cases like Henry Molaison, whom we discussed earlier. After losing the ability to form new long-term memories, Henry in many ways seemed stuck in time. He couldn't update his sense of self to account for new experiences. Each day was disconnected from the previous one. This suggests that ongoing memory formation is essential for maintaining a continuous sense of identity through time. But memory's relationship to identity is complex. You change over time, as everyone does. The person you are today is different from the person you were 10 years ago or will be 10 years from now. Yet you maintain a sense of being the same person, a continuous self that persists through all these changes. Your memories of your past self are part of what maintains this continuity. But those memories are viewed from your present perspective. You remember your past, but you interpret it through your current understanding, your current values, your current emotions. In a sense, you're constantly rewriting your own history, not by changing the facts necessarily, but by changing what those facts mean to you. This is particularly evident in how people's memories of their own past beliefs and attitudes tend to shift to be more consistent with their current beliefs and attitudes. If you once held political views that you've since changed, your memory of those past views tends to drift toward your current position. You might remember yourself as having been less extreme in your past beliefs than you actually were, or you might misremember when and why you changed your mind. This serves to maintain coherence in your life narrative. If you currently believe something strongly, it can be uncomfortable to remember that you once believed the opposite equally strongly. The memory system tends to smooth over these inconsistencies, creating a more coherent, if less accurate, personal history. As we approach the end of our exploration, it's worth reflecting on what all of this means for how we think about our past and ourselves. Memory is not a perfect record, but rather an active, dynamic process that serves our current needs and functions. Memories are constructed and reconstructed each time we recall them. They're influenced by our current knowledge, emotions, motivations, and contexts. This malleability of memory has both advantages and disadvantages. It allows us to learn from experience, to update our knowledge, to integrate new information with old. It allows us to extract meaning and patterns from our experiences. It allows us to maintain coherent life narratives and a sense of self. But it also means our memories can be inaccurate. Details can be forgotten or distorted. Events can be misremembered. False memories can be created. Our confidence in our memories doesn't guarantee their accuracy. Understanding these properties of memory can help us be more thoughtful in how we use memory and more humble in how much certainty we place in our recollections. It can help us appreciate the importance of external records and evidence. It can help us be more understanding when others remember shared events differently than we do. Can also help us be more intentional about what we choose to remember and rehearse. Since the act of recalling and retelling memories influences their content and accessibility, we have some degree of agency in shaping our memories. If you want to remember positive experiences, it helps to think about them, talk about them, perhaps journal about them. These acts of retrieval and elaboration strengthen those memories and make them more likely to be accessible in the future. Similarly, for negative experiences that might be unhelpful to dwell on, allowing them to fade through benign neglect might be adaptive. This doesn't mean repressing traumatic memories, which can be harmful. It simply means being thoughtful about which aspects of your past you choose to actively maintain through rehearsal and which you allow to recede. The malleability of memory might also offer therapeutic opportunities. If memories can be changed through reconsolidation, perhaps there are ways to reduce the emotional impact of traumatic memories or to modify maladaptive memories that contribute to psychological problems. This is an active area of research with some promising initial results, though much more work is needed to develop safe and effective therapeutic applications. Let's delve deeper into some specific mechanisms of memory change that reveal the intricate biological processes underlying how memories transform over time. Understanding these mechanisms at the molecular and cellular level provides a richer appreciation for just how dynamic memory truly is. At the most fundamental level, memories exist as patterns of synaptic connections between neurons. A synapse is the junction between two neurons where they communicate with each other. When a memory is formed, the synapses involved in representing that memory are strengthened. This strengthening happens through a process called long-term potentiation, abbreviated as LTP. Long-term potentiation was discovered in the 1970s by Tarja Lomo and Tim Bliss, who were working with rabbit brains. They found that if they electrically stimulated certain neural pathways repeatedly, the connections in those pathways became stronger and remained stronger for hours, days, or even longer. This was a breakthrough because it provided a cellular mechanism for learning and memory. LTP involves changes at multiple levels. In the short term, it involves changes in how efficiently neurotransmitters are released and received at synapses. Neurotransmitters are chemical messengers that carry signals from one neuron to another. When LTP occurs, neurons release more neurotransmitters, and the receiving neurons become more sensitive to those neurotransmitters. In the longer term, LTP involves actual structural changes. The synapses themselves can grow larger. New dendritic spines, tiny protrusions on neurons where synapses form, can be created. Proteins are synthesized that strengthen and stabilize these connections. These structural changes are why protein synthesis is so crucial for long-term memory formation and reconsolidation. Remember those experiments where blocking protein synthesis disrupted memory reconsolidation? The drug anhysamycin works by preventing ribosomes from assembling amino acids into proteins. Without new protein synthesis, the structural changes needed to stabilize a reactivated memory cannot occur, and the memory weakens. This protein synthesis requirement extends beyond just reconsolidation. Initial consolidation of memories also requires protein synthesis. If you block protein synthesis immediately after learning something, the memory will fade within hours even though it might seem fine initially. This is because short-term memory, which lasts for minutes to a few hours, doesn't require new proteins. But for a memory to be transferred into long-term storage, new proteins must be made. The specific proteins involved in memory are numerous and have been the subject of intensive research. One important class is the CREB proteins, which stands for cyclic AMP response element binding protein. CREB proteins are transcription factors, meaning they control which genes get turned on or off. When activated, CREB proteins bind to DNA and increase the expression of genes that are important for creating the structural changes underlying long-term memory. Animals that have been genetically modified to have more active CREB proteins show enhanced memory formation. Conversely, blocking CREB function impairs long-term memory. This has led to the idea that CREB functions as a kind of molecular switch for converting experiences into lasting memories. Other important proteins include those involved in the NMDA receptor system. NMDA receptors are a specific type of glutamate receptor found at many synapses in the brain. Glutamate is the main excitatory neurotransmitter in the brain. meaning it makes neurons more likely to fire. NMDA receptors have special properties that make them crucial for learning and memory. What makes NMDA receptors special is that they require both glutamate binding and depolarization of the receiving neuron to open. This means they only become active when there's coincident activity, when the sending neuron is active, releasing glutamate, and the receiving neuron is also active, being depolarized. This coincidence detection property makes NMDA receptors perfectly suited to implement the kind of associative learning where the brain needs to link events that happen together in time. When NMDA receptors open, they allow calcium ions to flow into the neuron. This calcium influx triggers a cascade of biochemical changes that ultimately lead to LTP and the strengthening of that synapse. Drugs that block NMDA receptors impair the formation of new memories, demonstrating their critical role in learning. Now, all of these molecular mechanisms provide the foundation for memory, but they also reveal why memory is inherently dynamic. Every time a memory is reactivated, these molecular processes are engaged again. The synapses that represent the memory become active, calcium flows, signaling cascades are triggered, and the opportunity for change arises. During reconsolidation, the memory trace is essentially being rebuilt using many of the same molecular mechanisms that created it in the first place. This rebuilding process is what creates the window of opportunity for updating the memory. New information experienced during or shortly after retrieval can be incorporated because the molecular machinery for modifying synaptic connections is engaged. This helps explain why studying the same material multiple times, spaced out over time, is more effective than one mass study session. Each retrieval opportunity engages these molecular mechanisms, strengthening the memory traces, but it also allows for updating and elaboration. You might notice new connections between ideas, understand concepts more deeply, or integrate the information with other knowledge you've acquired. Each study session isn't just reinforcing a fixed memory, it's actively reconstructing and enriching it. The brain doesn't just store individual facts or experiences in isolation. Instead, it's constantly working to extract patterns, to find connections, to build networks of related information. This process, called semantic memory formation, involves transforming specific episodic memories into more general knowledge. For example, when you first learned what a dog is, you probably encountered specific dogs in specific situations. Maybe you met your neighbor's golden retriever in the park, or you saw dogs in picture books, or you had a family pet. Each of these was an episodic memory, a specific encounter at a specific time and place. But over time, your brain extracted the common features from all these different encounters to form a general concept of dog. This semantic knowledge is abstracted away from any particular experience. You know what dogs are without necessarily remembering every individual dog you've ever seen. The episodic memories have been transformed into semantic knowledge. This transformation process involves systems consolidation and the gradual transfer of information from the hippocampus to the cortex. The cortex is better suited for storing these kinds of abstracted, schematized representations, while the hippocampus specializes in the rapid encoding of specific events. As memories age, they tend to become more semantic and less episodic. The specific details and contextual features fade, while the gist or general meaning is retained. This is why older memories often have a more generic, schematic quality compared to recent memories, which tend to be richer in perceptual and contextual detail. This transformation from episodic to semantic memory is another way that memories change over time. It's not just that details are forgotten randomly. Rather, there's a systematic process where certain types of information are preferentially retained while others fade. The brain regions involved in this process are themselves quite fascinating. The prefrontal cortex, the area at the front of the brain involved in planning, decision-making, and executive functions, plays a crucial role in organizing and retrieving memories. It helps control what gets remembered and what gets forgotten, and it's involved in the strategic aspects of memory, like using context to guide retrieval. Different regions of the cortex store different types of information. Visual information tends to be stored in visual cortex areas, auditory information in auditory areas, and so on. When you remember a complete experience, your brain must reactivate information distributed across these different regions and bind it together into a coherent memory. This distributed nature of memory storage is part of why memories can be so fragile. If one component of a memory is disrupted or lost, the entire memory might become inaccessible or incomplete. It's also why damage to different brain regions produces different patterns of memory impairment. For instance, damage to the left temporal lobe, which is involved in language processing, might particularly affect memory for verbal information while sparing memory for visual or spatial information. This dissociation shows that different types of memories are processed and stored in different brain systems. The study of patients with specific patterns of brain damage has been invaluable for understanding memory. Beyond Henry Molaison, many other patients have taught us about how memory works by showing us what happens when specific brain regions are damaged. Patient KC, studied by neuropsychologist Endel Tulving, had damage to his hippocampus and surrounding regions from a motorcycle accident. Like HM, KC couldn't form new episodic memories. But KC also couldn't remember any episodic memories from his entire life, even those from long before his accident. His semantic memory was largely intact. He knew facts about the world and about his own life. He knew he owned a certain car and where his family's summer cottage was located. But he had no personal, experiential memories of ever being in that car or at that cottage. This double dissociation between episodic and semantic memory supported the idea that these are distinct memory systems that can be selectively impaired. Casey's case showed that it's possible to know facts about your life without actually remembering living through the events that created those facts. Another instructive case is that of Clive Waring, a British musician and musicologist who developed severe amnesia in 1985 after contracting herpes viral encephalitis, an infection that damaged his hippocampus and other medial temporal lobe structures. Clive's case is similar to HM's in that he cannot form new long-term episodic memories. His short-term memory lasts only seconds. He lives in a perpetual present, constantly feeling as though he has just woken up for the first time. Remarkably, despite this profound amnesia, Clive retained his musical abilities. He can still play the piano and conduct a choir beautifully. This preserved ability demonstrates another dissociation in memory systems. Procedural memory, the memory for skills and habits, is supported by different brain regions than episodic memory, particularly the basal ganglia and cerebellum. These regions were largely spared in Clive's case, allowing him to access and even improve his musical skills even though he has no conscious memory of practicing or performing. These cases illustrate that memory is not a single, unified system, but rather a collection of different systems that can operate independently. Episodic memory, semantic memory, procedural memory, working memory, these are all distinct, though they interact and support each other in the intact brain. The interaction between these different memory systems is part of what makes memory so complex and dynamic. An experience might initially be encoded as an episodic memory, but elements of it might be extracted into semantic memory, contributing to your general knowledge. If the experience involves learning a skill, procedural memory systems will be engaged. All of these systems operate according to somewhat different principles and are subject to different types of changes over time. Working memory, which is the ability to hold and manipulate information in mind for brief periods, deserves special mention. This is the memory system you use when you're trying to remember a phone number long enough to dial it, or when you're following a complex set of instructions, or when you're doing mental arithmetic. Working memory has limited capacity, famously described as being able to hold about 7 items, plus or minus 2. However, this limit can be partially overcome through a process called chunking, where individual items are grouped into larger, meaningful units. For example, the sequence of letters FBICIANSA doesn't exceed working memory capacity when chunked into familiar acronyms: FBI, CIA, NSA. The prefrontal cortex is crucial for working memory, actively maintaining information in an accessible state through sustained neural activity. Working memory is where information is consciously manipulated before potentially being encoded into long-term memory. The quality of working memory processing affects how well information is encoded. Deeper, more elaborate processing in working memory generally leads to better long-term retention. Interestingly, working memory capacity shows individual differences, and these differences correlate with various cognitive abilities. People with greater working memory capacity tend to perform better on reasoning tasks, reading comprehension, and other complex cognitive activities. This suggests that working memory isn't just a passive holding area but an active workspace where important cognitive operations occur. The relationship between working memory and long-term memory is bidirectional. Information from long-term memory can be brought into working memory for conscious manipulation. And information in working memory, if attended to and processed sufficiently, can be consolidated into long-term memory. This constant interplay between different memory systems is part of what makes memory so dynamic. Another factor that influences how memories change is the phenomenon of interference, where some memories interfere with the formation or retrieval of other memories. There are two main types of interference: retroactive interference, where new learning interferes with old memories, and proactive interference, where old memories interfere with new learning. Retroactive interference is what happens when you learn someone's new phone number and subsequently have trouble remembering their old number. The new information overwrites or makes it harder to access the old information. This is particularly likely when the old and new information are similar, as they compete for representation in the same neural networks. Proactive interference works in the opposite direction. If you've known someone by one name for years and they change their name, you might keep accidentally using the old name. The old, well-established memory interferes with your ability to consistently retrieve and use the new information. Interference is a major cause of forgetting. It's not necessarily that the memory trace decays or is lost. Rather, it becomes harder to access because other, competing memories interfere with retrieval. This is why forgetting often isn't permanent. Memories that seem lost can sometimes be recovered with the right retrieval cues or enough time passing for the interfering memories to weaken. The spacing effect mentioned earlier in the context of studying relates to interference. When you space out your study sessions, you reduce the amount of interference between them. Each session is distinct, occurring in a different context and mental state, which helps keep the memories from interfering with each other and promotes better integration of the material. Sleep's role in memory extends beyond just consolidation. Sleep also appears to help protect memories from interference. When you learn something and then sleep before learning something else, the first learning is better retained than if you stayed awake and learned new information immediately. Sleep provides a period of reduced interference where memories can consolidate without competition from new incoming information. This has practical implications. If you're trying to learn something important, learning it before sleep rather than before a busy day of new experiences gives those memories a better chance of consolidating effectively. Similarly, if you're studying multiple subjects, spacing them out and including sleep between study sessions can reduce interference and improve overall retention. The concept of context-dependent memory adds another layer to understanding how memories change and why retrieval can be variable. Memories are not stored in isolation. They're encoded along with the context in which they were experienced. This context includes the physical environment, your emotional and physiological state, and other aspects of the situation. When you later try to retrieve a memory, your success can depend partly on how well your current context matches the encoding context. This is why returning to a place where something happened can trigger vivid memories of that event. The physical context serves as a retrieval cue, reactivating the memory. This principle has been demonstrated in many experiments. In one classic study, participants learned information either on land or underwater while scuba diving. They were later tested on the information either in the same environment where they learned it or in the different environment. Performance was best when the learning and testing environments matched, demonstrating context-dependent memory. Similarly, state-dependent memory refers to better retrieval when your internal physiological state matches the state you were in during encoding. If you learn something while caffeinated, you might remember it better when caffeinated again. If you learn something in a particular mood, that mood can serve as a retrieval cue later. These context and state dependencies mean that the same memory might be more or less accessible at different times depending on your current situation and state. This variability in access is another way that memory is dynamic. The memory itself hasn't necessarily changed, but your ability to retrieve it varies with context. Over time, as memories become more consolidated and less dependent on the hippocampus, they may become less context-dependent. Well-learned information can often be retrieved across a wide range of contexts. But recently formed memories, still heavily dependent on hippocampal processing, tend to be more tied to their encoding context. This progressive decontextualization is another way memories change with time. A recent memory might be rich in contextual detail, strongly associated with the specific time and place and circumstances in which it was formed. An older memory of the same event might retain the core information but lose many of these contextual details, making it more abstract and less tied to specific circumstances. The role of attention in memory cannot be overstated. What you pay attention to during an experience strongly influences what you'll remember later. The brain has limited processing capacity, so attention acts as a filter, determining what gets deeply processed and encoded versus what's only superficially registered or ignored entirely. This selective nature of attention means that two people experiencing the same event can form quite different memories of it because they attended to different aspects. If one person was focused on the conversation they were having while another was focused on the visual surroundings, their memories of the event will emphasize different features. Moreover, attention during retrieval also matters. When you're trying to remember something, focused attention helps. Divided attention, like trying to remember while also doing other tasks, impairs both encoding and retrieval. This is why studying while constantly distracted by notifications or multitasking leads to poorer learning than studying with focused attention. The interaction between attention and memory has important implications for eyewitness testimony. Witnesses to crimes are often in highly arousing, stressful situations where their attention might be narrowly focused on certain details, like a weapon, while missing other potentially important information. This weapon focus effect has been demonstrated in numerous studies. When a weapon is present, witnesses tend to remember it vividly but have poor memory for other details like the perpetrator's face. Stress and arousal more generally have complex effects on memory. Moderate levels of arousal tend to enhance memory encoding and consolidation. This is the emotional enhancement effect we discussed earlier, mediated by stress hormones and amygdala activation. But very high levels of stress can impair memory formation, potentially causing fragmented or incomplete memories. Chronic stress can also impair memory. Prolonged elevation of stress hormones like cortisol can actually damage the hippocampus, shrinking it and impairing its function. This is one reason why people with depression, which often involves dysregulated stress hormone systems, frequently experience memory problems. The relationship between stress, emotion, and memory is clinically relevant for understanding post-traumatic stress disorder, or PTSD. In PTSD, memories of traumatic events are often fragmented and disorganized, lacking the normal narrative structure. Yet these memories can be intensely vivid in certain aspects and can intrude into consciousness as flashbacks or nightmares. The fragmentation may result from the very high levels of stress during the traumatic event disrupting normal hippocampal processing. The hippocampus, as we've discussed, is responsible for binding together the different elements of an experience into a coherent episodic memory. Under extreme stress, this binding process may be impaired, resulting in disconnected fragments rather than an integrated memory. Recent therapeutic approaches for PTSD have tried to leverage reconsolidation mechanisms. If a traumatic memory can be safely reactivated in a therapeutic context and then reconsolidated with less fear and better emotional regulation, the memory might be modified to be less traumatic. This is still an area of active research, and the results have been mixed, but it represents an application of basic memory science to clinical problems. The study of memory in animals has been crucial for understanding these mechanisms. Obviously, you can't do many invasive experiments on human brains, so animal models, particularly rodents, have been invaluable. Much of what we know about the molecular mechanisms of memory comes from studies in rats and mice. However, animal research has limitations. Animals can't tell us about their subjective experience of remembering. We can't ask a rat whether it remembers a specific past event in the way humans experience episodic memory. What we can do is observe their behavior and neural activity and infer what kinds of information they've stored and can retrieve. One fascinating finding from animal research is the discovery of place cells and grid cells in the hippocampus and nearby brain regions. These neurons fire selectively when an animal is in particular locations in its environment. Place cells form a kind of cognitive map of space, and they're thought to be crucial for spatial memory and navigation. But place cells also fire during sleep, often in sequences that correspond to paths the animal took while awake. This replay of spatial experiences during sleep is thought to be part of the consolidation process, helping to strengthen memories of important locations and routes. Interestingly, place cells can also fire in novel sequences during sleep, paths the animal never actually took but that represent plausible routes through its environment. This suggests that the brain during sleep is not just replaying experiences but also creatively combining elements to imagine new possibilities. This might be related to how we consolidate not just specific memories but also extract general knowledge and make inferences. The discovery of place cells, which earned John O'Keefe, Maybert Moser, and Edvard Moser the Nobel Prize in Physiology or Medicine in 2014, opened up new ways of studying how memories are represented in the brain. Researchers can now track the activity of identified neurons representing specific memories and watch how that activity changes during consolidation, reconsolidation, and retrieval. Studies using these techniques have shown that memories are not static. The ensemble of neurons active during encoding of a memory isn't necessarily the same ensemble active during later retrieval. The representation can shift, with some neurons dropping out and others being recruited. This remapping is yet another way that memories change at the neural level. Technology has advanced to the point where researchers can now manipulate specific memories in animals. Using optogenetics, a technique where neurons are genetically modified to be responsive to light, researchers can selectively activate or inhibit the specific neurons that represent a particular memory. In landmark experiments, researchers have reactivated fear memories artificially, causing mice to freeze in fear even though nothing threatening is present, just by activating the ensemble of neurons that represent that memory. They've also successfully created entirely false memories, making mice fear a context they were never actually shocked in, by artificially activating memory neurons during a shock in a different context. These experiments provide dramatic demonstration of the neural basis of memory and show that memories are indeed constituted by the activity patterns of specific neural ensembles. They also show how malleable these representations are. They can be artificially created, modified, or suppressed. Of course, human memory is far more complex than mouse memory. Humans have language, abstract reasoning, complex social cognition, and many other capabilities that go beyond what can be studied in rodents. But the basic mechanisms, the molecular processes, the role of structures like the hippocampus, these appear to be conserved across mammalian species. Studying memory in humans necessarily relies more on behavioral methods and non-invasive brain imaging. Functional MRI allows researchers to see which brain regions are active during different memory tasks. EEG and MEG provide information about the timing of neural activity with millisecond precision. These techniques have revealed much about human memory. For example, fMRI studies have shown that true and false memories activate largely overlapping brain regions, which helps explain why false memories can feel just as real as true ones. The brain's activity patterns don't necessarily differ in ways that would allow someone to introspectively distinguish a false memory from a true one. Brain imaging has also revealed the neural correlates of the reminiscence bump. When older adults remember events from their youth, their brain shows patterns of activity in regions associated with reward and emotion processing. This suggests that these memories may be particularly pleasurable or meaningful, which might be part of why they're well retained. The future of memory research likely involves increasingly sophisticated techniques for measuring and manipulating neural activity, combined with computational models that can help make sense of the vast complexity of memory processes. Understanding memory at a mechanistic level might eventually lead to interventions to enhance memory in cases of impairment or to reduce intrusive memories in conditions like PTSD. But memory research also raises philosophical questions. If memories are constantly changing, constantly being reconstructed, what does this mean for personal identity? What does it mean for legal concepts of testimony and evidence? What does it mean for historical truth? These are not questions that neuroscience alone can answer, but understanding the science of memory is crucial for thinking about them thoughtfully. We can't address questions about the reliability of memory without understanding how memory actually works, with all its flexibility and fallibility. The practical applications of memory research extend to education. Understanding how memory works should inform how we teach and how we learn. The testing effect, spacing effect, the importance of sleep, the role of attention and meaning in encoding, all of these findings from memory research have clear implications for educational practice. Yet many educational approaches don't fully incorporate this knowledge. Cramming before exams is still common, even though spaced practice is demonstrably more effective for long-term retention. Passive rereading is a common study strategy, even though active retrieval is more effective. There's often a gap between what research shows works and what people actually do. Part of closing this gap involves education about memory itself. When students understand how memory works, they can make more informed choices about how to study. When teachers understand memory principles, they can design instruction that works with the brain's natural learning mechanisms rather than against them. Memory research also has implications for how we think about aging. Memory decline is often seen as an inevitable part of getting older, and indeed, some aspects of memory do tend to decline with age. Older adults often show reduced working memory capacity and can have more difficulty forming new episodic memories compared to younger adults. However, not all aspects of memory decline with age. Semantic memory, general knowledge about the world, often remains stable or even improves with age as people accumulate more knowledge and experience. Procedural memory for well-learned skills tends to be well preserved. And as mentioned, older adults often show a positivity bias in memory, remembering more positive information and experiences. Moreover, the extent of age-related memory decline is variable. Factors like education, physical activity, social engagement, and cognitive stimulation all appear to help maintain memory function in older age. The brain retains plasticity throughout life, and continued learning and engagement can help preserve and even enhance cognitive function. Understanding the neuroscience of memory also helps clarify the distinction between normal age-related changes and pathological decline as seen in Alzheimer's disease and other dementias. Normal aging might involve some slowing of processing and some difficulty with certain types of memory tasks, but it doesn't involve the severe, progressive impairment seen in dementia. Alzheimer's disease, the most common form of dementia, is characterized by the accumulation of abnormal proteins in the brain, particularly beta-amyloid plaques and tau tangles. These proteins particularly affect the hippocampus and cortex, regions crucial for memory. This is why memory impairment, especially difficulty forming new memories, is often an early sign of Alzheimer's disease. Research into the basic mechanisms of memory has contributed to understanding neurodegenerative diseases and to the search for treatments. While we don't yet have a cure for Alzheimer's, understanding how memory normally works and how it breaks down in disease provides crucial insights for developing interventions. As you drift towards sleep tonight, your brain will engage in its nightly work of memory consolidation. The experiences you had today will be replayed, processed, integrated with existing knowledge and memories. Some will be strengthened and retained, others will fade. The person you wake up as tomorrow will have slightly different memories than the person falling asleep tonight, as your brain continues its endless work of constructing and reconstructing your past. This process has been going on every night of your life, shaping and reshaping your memories, your knowledge, your sense of who you are. It will continue throughout your life, allowing you to learn and adapt, to maintain a sense of continuity while also growing and changing. The past is not fixed and unchanging, preserved perfectly in memory. Instead, it's constantly being reconstructed, reinterpreted, reimagined in light of the present. Your memories are not just records of where you've been. They're tools you use to navigate where you're going. Understanding the dynamic nature of memory, its reconstructive processes, its vulnerabilities to error, its remarkable functions and capabilities, this understanding enriches our appreciation for the complexity of the human mind and the fascinating mechanisms that allow us to learn from experience and maintain a sense of ourselves through time. The journey through the science of memory reveals that remembering is not a passive replay of the past, but an active, constructive process. Each time you remember, you are not simply accessing a file but rebuilding an experience, influenced by your current knowledge, expectations, and context. This reconstruction can introduce changes, subtle or significant, that alter the memory from its original form. Yet this very malleability that makes memory fallible also makes it functional. A rigid, unchanging memory system might preserve perfect records of the past, but it would be less useful for learning, for adapting, for extracting meaning from experience. The flexibility of memory allows you to update your knowledge, to learn from new information, to integrate different experiences into coherent understanding. Memory is fundamental to almost everything we do. It allows us to recognize faces, understand language, navigate familiar environments, maintain relationships, pursue goals, enjoy stories and art. Without memory, there would be no learning, no accumulation of knowledge, no sense of personal history or identity. And yet, for something so fundamental, memory often works quietly in the background, only drawing our attention when it fails. We notice when we forget something important or when we're caught off guard by a vivid, unexpected recollection. Most of the time, though, memory just works, providing us with the information we need when we need it, usually accurately enough for our purposes. Appreciating the science behind this everyday miracle, understanding the neural machinery, the molecular mechanisms, the psychological processes that make memory possible, this deepens our sense of wonder at the capabilities of the human brain. It also makes us more thoughtful about memory, more aware of its limitations, more humble about our confidence in our recollections. If you found this exploration of memory illuminating, consider subscribing for more gentle journeys through the fascinating landscape of science and the human mind. There are countless wonders to discover in how our brains and bodies work, countless questions to explore about consciousness, cognition, and what it means to be human. Until next time, rest well, and may your sleeping brain do its quiet work of memory consolidation, weaving the threads of today into the fabric of your ongoing life story, creating memories that will guide and shape you in ways both subtle and profound. Sleep peacefully.